Good morning, Leafy. John is not here yet. Okay, so uh, today we'll discuss about queuing theory. Okay, so you can follow this in Lentera. Okay, so I think this is game theory. We finished everything already, and last week we started a little bit about game theory. So this is the one that we will discuss. Seems like a lot, but actually only the first and the last two probably that is really significant. The others are, I already have the website, okay, that I created this. So you can search in queuing and follow to queuing theory follow to in Google. Okay. So what happened to this? Anyway, so in this website you can see I have a calculator, okay, for each of the things that we discuss here. So you can also use, say for example, this one. So okay, optimize so you can calculate directly here. Okay. Okay, let's start with our lesson. So we start with basic queuing theory and measurement of effectiveness. So again, I will discuss what is queuing and then what is queuing theory, and we discuss about this following topics. I will touch a little bit about Kendall notation, and then what is measurement of effectiveness, okay, where the queuing theory come from, and then certain fundamental formula, as well as my own rule of thumb, okay, so that you can use this theory in practice. Yeah. Okay, so at least this is the one that you should be able to do. So you should comprehend input and output of queuing theory, understand the elements of queuing theory, and fundamental queuing formula. So why we talk about these objectives? Because these are the ones that will be in the exam. Yeah? Okay, so basically when you do some theory, you want to know, okay, the numerical value, okay, of the performance, okay, of the system. So what we have here is a queuing system. So you as the management can use one of the following methods. Yeah? One is to do direct observation. Okay? So get the data and then calculate the system statistics. Okay? We will discuss about it today. And then we also can do another alternative, which is based on queuing theory, or we will do simulation. We will not discuss simulation in this class. And the last one, for practical reason, I will just discuss the practical queuing or rule of thumb that I developed. Okay, so any queuing system will have these two things. One is the input and the output. Okay, the input is basically a customer and service. Okay, so the input are two, okay, customer and service. So the customer represent the demand. Okay, the services represent the supply. Okay, so in the customer, you probably want to know at least two things. Okay, at least so you can know more than that. So at least you need to know two things: arrival process. Okay, what are the arrival process? In the arrival process, you want to know what is the arrival rate and the distribution pattern of that arrival process. Okay. Second, of course, in the customer, you want to know the population, whether it's finite or infinite. Okay. Based on these two, okay, you will have a various type of queuing system. Okay. Similarly, with the services, okay, you want to know again the service rate and distribution pattern of the service rate, and then what is the configuration of the service, okay, whether it's parallel cereal and mix and so on. And then you want to know the queuing capacity, okay, waiting capacity. Okay. And then the service discipline. So these are the usual input for the queuing system. Okay. And the output, we call this as measurement of effectiveness or operating characteristic or simply performance measure. Okay. Next, you can actually generalizing the queuing problem as demand and supply problem. So the whole logistic system from distribution, yeah, for example, from the factory to the warehouse to the agent, for example, yeah, and then to the retailer, and finally to the customers. These are actually based on queuing system also. Okay, and each part is actually a queuing system that connected through a network of series or parallel. Okay, so similarly, if you have a restaurant, for example, okay, there is an order, right, and then you cook. After that, you serve, right. Then there is a cashier, and then after that, you clean, and then you purchase some materials. Each of these, again, are a queuing system that you can model. Okay. So, so I define the customers. So the demand here is basically the user that's seeking the entity for service. So this can be people, can be job, can be vehicles, can be whatever. Right? While the server, the demand, the supply here, is anyone or anything that provides the service. Okay, so of course inside the server, if this is a physical server, usually we have what is called station. So station is just location where the single line of will form in front of one or several server. Okay, so look at the traditional queuing system. Okay, the customer will arrive in the queuing system and then waiting, right, in the waiting line to be served. Okay, while after that the customer will be served. Oh, did I record this? Yes.
Yes, sir.
Yes. Okay, and then
Mm-hmm.
uh, while being served, okay, the customer usually transfers some information to the server. So, for example, the order, the item to be purchased, the ID, and so on. Okay, and then the server will probably input this customer data, okay, using scanner or maybe typing the data, and then the server will do some order processing. For example, preparing the items. In the cashier will get the money, okay, and order some processing, and then the server will transfer the material or the information to the customer. Yeah? So this material or information can be in terms of receipt, change, the food or document, and so on. Right? Finally, the customer will finish being served and then exit the system. Yeah? This is talking about one queuing server, yeah, one station, okay. And then the customer will go to the next stage of the queuing system. Okay. So if you look at this, okay, there are a lot of transfer of information, right? So that means if you can separate the material from the information, you can actually reduce the queuing time. You get it? That's the basic idea there. Okay, so what I propose, okay, is to generalize what is the meaning of queuing. Okay, usually queuing in many textbook, you will see queuing is basically waiting line. So now I try to generalize this definition of queuing based on the purpose of transferring the information, okay, material or people or things between the customer and the server. So it's not just the waiting line. Okay, so with that we can say that generalized queuing is a process, okay, where things here can be materials, okay, people, okay, or information that need to wait at certain time to get the service. Yeah? So now, when we study the queuing theory, basically we study about parallel services. So these are the main themes in this topic of queuing theory. Okay, so look at this. This is the traditional queuing theory. So basically queuing is just arrival and then they wait and then being served and then exit, right? So, but once you generalize this, okay, so then you can see that queuing is a process, okay, where it's okay. So where people, material, or information need to wait to get the service. So, okay, instead of waiting line, so you generalize the queuing is a process of things that wait to get the service. Okay? So with that abstraction, then you can start to think of anything is a queuing system. Okay? Anything that need to wait is a queuing system. Is it clear or not?
Yeah, it's clear.
Okay, so next. So what is queuing theory itself? Okay, so queuing theory is just a body of knowledge dealing with waiting line. Right? So again, this is traditional view. Okay, so this mathematical model, okay, representing a system that provides a service to the customer, okay, whose arrival time is random. Okay, so imagine it started more than 1 century ago, right? But until now, we did not actually solve the queuing problem, right? So, and then that's why we need to propagate this knowledge, okay? Not just to you. So I hope you can also propagate this knowledge to many people. Okay? So this is very important problem that we face in daily life. For example, traffic is the one that we face every day, right? I think you are late because of traffic. Yeah? So so this is very related to our daily life. Okay. So now, say I have. Can you see this? There's a pointer here. So this is a queuing system of one server in this top drawing. You see it? So you have one server, okay, and then this is the waiting line, and then this is the customer being served. Okay, after finished, it will go out of the system, right? So then this is multi-server. This is parallel server, right? So there are two systems. Okay? One is this. You have a customer waiting in a single line, and then whenever first of this server finish, they will go to the server that is finished. Or the second is, look, every server will create a waiting line. So my question to you is, which one is better? Which one is better in terms of performance? So then, okay, before that, before we continue, okay, can you think? Can we discuss? What do you think? Which one is better?
Isn't it the second one?
The second one. This one is better.
No. The
Oh, this one. This is better.
Yeah.
Oh, tell me why. Why this is better than the last one here?
Yeah, because I see a lot in the
because you used to this system, because you see a lot.
Yeah, even in the airport, yeah, we do that, right?
Okay. So when you see a lot doesn't mean it's good, right? Right.
But
Yeah, the bottom one is also a lot, the normal queuing one. So what make them different? This is the one that you will try to analyze. And how to analyze this, right? That's the point. How you analyze these two? Okay, how are they different? How are you going to calculate these two? Okay, this is the one that we need to study. Okay, so this is tricky question. Yeah. So when I said which one has better performance, so I did not mention what is the performance here. Okay, so which one has better performance? What is the performance first? Okay, so in terms of queuing length, yeah, in terms of queuing length, this is definitely better, right? Yeah. So because shorter queuing length, yeah. Okay, but so this one become very long. Yeah. Say the number of customers is the same. Okay, say 100 customer, in here is also 100 customers. So in terms of queuing length, this is very long, 100. Here is probably divided by 10 or divided by 3 in here, right? So in this case, maybe 30, 30. So the length here is worse than this one. Okay? But in terms of queuing time, okay, this is probably better. But again, that depends also on the distance, the distance between this queuing to this server. Eh? So if the number of server, for example, very big, okay. So if you have only single waiting line like this, and then the walking distance is too long, that also will deteriorate because the customer need to walk, for example, from this waiting line to the server. That takes time, right? So again, if the distance is not so long and negligible, okay, so this is the, in terms of time, the delay, this is better than this one. Okay? In general, okay, I'm just talking in general. So the detail you need to calculate. Okay, so again, better performance in terms of walk. Okay, so this is tricky. Okay, so going to the queuing theory, so I will start with a very simple notation first. Okay, actually the real notation have 6 numbers here, but I will simplify it first. Okay, I will simplify it with only 3 numbers, with A, B, and K. Okay, this notation is proposed by Kendall in 1963. Okay? This is to classify. There are so many type of queuing, right? There are so many type of queuing. So how are we going to classify? Okay? Remember, 1917 was proposed by Erlang, but almost 50 years later, okay, they start to classify. So this is quite long. Okay, and how do we classify? A represent the demand. Yeah? And in this case, we talk about probability distribution of the arrival. Okay? And then B is the probability distribution of the service time. So this is the supply. Okay? And K is the number of channel. What is this? This is the parallelism. Okay? Parallel server. Important here is to understand, we talk about queuing is talking about parallel. Okay, this is what I feel many people hard to understand when they talk about parallel, because they think queuing just in terms of one server always. They don't think in terms of parallel. So, but you look at the symbol, the basic symbol of Kendall notation here. In the beginning, we already talked K here is the number of channel. That means parallel server. Okay. Keep in mind, this is talking about parallel. So later on, when you see the real world problem, okay, they always think in terms of serial system, not parallel system. That's why the queuing still exists, because they don't. The way of thinking is wrong. Okay. Okay. let's back here to the A and B here. A and B, yeah, there is no real A and B. Okay, this is just my own notation. In this A and B, you can replace this with either M, G, C, or whatever letter that we agree upon. Okay, so when we said M, here mean is Poisson process. Mean the probability distribution of arrival will be Poisson. Okay, but the probability distribution of service time will be exponential. So Poisson process, okay, Poisson process meaning for arrival will be Poisson, for service time will be exponential. These are the two are the same thing. Did you know these two are the same thing in statistics? Did you learn that? Okay. So okay. Later I will discuss more detail about this. Yeah. So next is there is also possibility that they are not random. Okay. What is the meaning of Poisson process? Meaning this is random. Okay. Random distribution. Okay. And then later we will discuss more detail. What is random mean? Okay. So next is deterministic. Okay. So for example, what is the possibility of deterministic? Okay. Say if they are machine, okay, in the factory, so the arrival come from the machine, that means constant, right? So deterministic not necessarily constant, can be linear, okay? So, but there are certain rule that is not random, okay? So mostly constant. So example again, traffic signal. So this is the service that is actually cyclical, right? You know, traffic signal have certain time. Okay, that means the service time is a constant. So that is T. Okay. So if you don't know, okay, they are not Poisson. Okay, then you, if you want to use queuing theory, then you probably want to use probably they are general distribution. Okay? So in this case, we approach it through normal distribution. So we say that probably we know the mean and the variance. Okay, the mean and the variance are clear. So again, Kendall notation. Okay, A and B you can replace by M, D, or G, or something else. For example, Erlang distribution we will put E. Right? So, but in our course we will just talk about these three. Okay? Actually less than that, mostly about M. Okay, is it clear or not? When I said about Kendall notation. Okay, yeah? Okay, next. So this is example. Okay, DD1. What is this? Deterministic. 1. What is this? The arrival is deterministic. Yeah? The service is deterministic, and then 1 is the number of server is only 1. Okay, so this is a special. This is a special. So when your DD1, okay, they will have no queue unless the arrival rate is actually larger than the service rate. Okay, so this is a special thing. But whatever you have random here, okay, is the other way around. Okay, when the arrival rate is larger than the service rate for this other queuing system, the queuing will go to infinity. Okay? So only DD is the one that make a queue when the arrival rate is larger than the service rate. Can you remember that? Please take a note. Huh? Okay, only when deterministic, then the arrival rate must be larger than service rate. But if the arrival or the service rate is random, so MD, MM, okay, DM, so all of these, the service rate must be smaller than the arrival rate. Is it okay? Okay, please take note. I did not put here, but that is very important to know because later you will start to realize when you input into the queuing system the formula. Okay, so MMS, what is the meaning? Random arrival, random service time. Okay, and then the number of server is S. Okay? MDS is example of traffic signal. S in here is the number of lane. Okay. So the doctor appointment system is DMS. Okay. So the arrival of the customer is based on the appointment. So D, deterministic. But the doctor doing something is unclear when they will finish. So it's M. Right. S is the number of doctor. Okay. So if you don't know, MG1 is the example of random arrival, and then the general distribution for the service time. Okay, that means you have a certain mean and variance here. Okay, so how do you know this is random? This is important. Okay? Take a note. Random or Poisson distribution, okay, have characteristic that the coefficient of variation is almost 1 or near to 1. What is coefficient variation? Standard deviation divided by mean. Okay, so how about deterministic? Okay, the characteristic of deterministic is the coefficient of variation is close to 0. Okay, so otherwise, okay, for example, if the coefficient of variation is very big, so probably you will say, okay, that is general. Is it or not? So if you said, okay, how I know it's random or not? Okay, of course you will check the distribution, okay, using goodness of fit in statistic, okay. But in general, if you don't know the distribution, okay, and you just check the mean and the variance, and then you calculate the coefficient of variation, then you can guess already. Is it or not? This is the practical way to do. Okay. Again, I'm talking about rule of thumb here. Is it clear?
Yeah, it's clear.
Clear, yeah? So, next, in queuing type, now depends on the population. So, population means the demand, okay? The demand, the user, the customer. So, is it finite or infinite? Okay, so if in general it's infinite, meaning you don't know how big is the number of customers, right? In general, if you don't know, so assume infinite. Okay? But if you know the number of customer, for example, the customer is a machine, or the customer is actually the repairman, or the machine to the repairman, right? The number of machine is finite, right? Not so many. So maybe 10 machines, and then the repairman will be the one that repair that machine. So in that case, the number of population, the customer is machine, right? So the number of population is finite. So that is totally different queuing system. Okay. So if we don't say that the customer is finite, so then you need to assume they are infinite. Okay. Next, the customer, okay, is the inflow, right, coming to the system. So the way in which the arrival of the customer occur over time. So in this case, you will take the mean, okay, the mean average, meaning mean is the average, right? The mean of arrival rate. So that mean of arrival rate usually say the per hour, the unit is customer per hour, right? But you can also measure it as headway. So this is the important part here. Okay, I will write here. So this is basically flow. Okay. So flow rate, right? This is the flow. Flow is basically 1 over headway. Yeah? Yeah? This is the mean. So the flow is 1 over headway. What is it headway here? Headway is something like this. This is, suppose this is a car, okay, going to that direction. Okay. So how you measure the flow? The flow you will measure by 1 point here. Okay, this is your eyes. Okay, looking at how many car will pass through that line per minute or per hour. That is called flow. Okay, so you will create an imaginary line. Okay, okay, and then how many cars will pass that line, that is called flow. Clear, yeah? So sometimes people confuse between flow and density, you know. They will say, oh, a lot of traffic because a lot of car in the road. That is not flow. In fact, a lot of car maybe they stop moving, right? The flow is 0. Right? Why? Because there is no car passing that line. Okay? The flow is not the same as density. Density is the number of customer or maybe the car per space, no? Per kilometer or per square meter. Okay? That is density. So flow, in other hand, is the number of customer per time. Is it clear? The meaning of flow. Okay. Next is the headway. What is headway? Headway is the time between customers. So usually we would talk about the bumper here, the bumper and the bumper here. Okay. So instead of, so you use the same observation. So this is your eyes. Okay. So instead of measuring, instead of counting the number of customers that pass, you are measuring the time between one customer to the next customer. Is it clear or not? Okay. So headway is inter-arrival rate. That means the mean of the time. Okay. So the unit is minute per customer. No? Okay. Minute per customer or second per customer. Okay. So time per customer. So that's why we can say that actually the average of headway, okay, the average of headway, 1 over the average of headway is the same as the flow rate itself. Is it clear now? Now, when you measure the flow, okay, and the distribution is say Poisson, right? Then of course 1 over Poisson is exponential. So that's why earlier I said, look, Markovian, we call it Markovian, because basically Poisson distribution and exponential distribution is just 1 over. Yeah, just reciprocal. Is it clear now? Okay, so the arrival rate is the total number of customers arriving in n unit time divided by n unit time. Yeah. So inflow, other name is demand. Yeah, customer arrival distribution flow rate, arrival rate, they are the same meaning. Okay. Just be careful with the units. Okay. If it is per hour, so all the others must be per hour. If they are per minute, so must be all per minute. So the same thing. Clear? Okay, let's make a practice of this. So I collected data. Okay, 2,400 customer arrived in 200 hours. So what is the arrival rate? You see, right? Yeah. So just 2,400 divided by 200. Yeah. So that is 12 customer per minute. Okay. Per hour. Yeah? 12 per hour. Okay. So, this is important discussion. Sometimes in the queuing system that you're dealing, you don't know which one is customer, which one is server. Okay, so you need to check, okay, who are the customer in your system. Okay, is it car, maybe truck, maybe the ship, maybe the buyer, maybe the clients, maybe the members, no? Or the goods itself, or maybe the machine, or the number of calls, okay? Maybe the bits. So you need to identify who are the customer in your system, okay, and what is the characteristic. Okay, so are they required to join the service or not? Compulsory, yeah? Or is there any competitor? Okay, and is the demand stationary or not? Are they the same type? Belong to the identical distribution or not? So by identifying this customer, okay, then you start to realize many things. Okay, so what is their behavior? Okay, do they actually argue, yeah, and chat with the server? Are they angry if they are waiting too long? Okay, do they come in the group or individual? Totally different behavior, right? For example, in the family restaurant, okay, we are talking about group here. The customer is actually a group, not just individual, right? So behavior is totally different with individual customer. Okay, and then is there any serial correlation exist? What is the inter-arrival time? Okay? Are they independent or dependent to each other? Yeah. So there is possibility that when the customer arrive, okay, their depends on the previous arrival, right? So some correlation exists between inter-arrival time to the queuing line because they actually come from the other queuing. So that will have different behavior as well. Okay, so if you cannot do the using queuing theory, then the only way to solve is using simulation. Okay? That is the last resort. And then you check, okay, whether the demand is actually fluctuation or not. Okay, so which day of the week, right? And then shall we compute only the peak hour or the whole day, right? So how about the demand for the big event? For example, Hari Raya, okay? So that is a big event that many people will go home, right? Then the fluctuation is totally different. Then you probably want to analyze differently from the normal event, right? The rare event will be analyzed differently from the normal event. So next is the distribution of the demand. Okay. Now, this is happened in DD1. Okay, in DD1. Queuing only happen when the arrival rate is actually larger than the service rate. Okay, or DDS is the same thing. So I will give name lambda represent the arrival rate. Okay, mu we call this service rate. Okay, so rate mean the mean. Okay, so the worst case will be the pure random. Okay? The worst case will be the pure random, which is MM1. Okay, where the arrival rate is actually larger than the service rate. Okay, but when we count the whole day, actually the lambda over mu is less than 1. So in this case, the Q will form even if the lambda over mu is less than 1. Okay, so in MM1, anything with M, okay, or general, the arrival rate less than service rate. Okay? But only in deterministic and both deterministic in terms of arrival and the service, then queuing will only happen when the arrival is larger than the service rate. Why? Okay. Why? Because in any random, you can have some kind of peak hour demand. Okay? So the peak hour demand happen at that time, and then you can have a off peak. Okay? When the queue is diminished, so then you can have a reduce of the demand, that the server will start to finishing all the queue. Okay? But when they are both arrival and service rate is deterministic, that is not possible to finish the demand, right? So that will continue to become infinity. Okay. So up to here, is there any question first before I continue? Okay, tell me what you learned so far. I cannot hear you, Vivi.
Okay, so I learned the queuing. The queuing, it's not just like the what is it, the line, a line, waiting line, and then this, it can also be parallel. It means the server it's more, can be more than one.
Yes.
And then we also need to determine the, what is it, the our customer, and then their characteristic, and then we can know the flow rate. Yeah. And
From the Joy, what you want to say something? I will close my. Candle notation, yeah. You. Less than the. Right. Yeah, yeah. So distribution, right? Okay, so let's continue. Okay, more detail now. This, can you see? Now we talk about arrival distribution. Most common type is actually Markovian and deterministic. Okay, Markovian means Poisson process. Okay, so I put here, if the number of arrival in a given period of time occur randomly and independently from other arrival, and it follow Poisson distribution with the mean of lambda customer per time, so the time here is minute, then the inter-arrival time, that is the headway, will follow the exponential probability distribution with the mean of 1 over lambda minute. Clear, yeah? This is just repeating what I'm saying earlier. Okay? So Poisson distribution and exponential is just 1 over the other. So we talk about completely random arrival. So each customer, when not in the system, okay, make a demand uh, on the system at completely unpredictable time. Okay, and they are independently from the other customer. Okay, at the given same rate. Okay, so random means unpredictable. When they will come, you don't know. Yeah. So let's practice this a little bit. Okay. The arrival rate is 12 customer per hour. Oh. What is the average inter-arrival time in minute? Inter-arrival time means the average time between two consecutive arrivals. Oh, can you calculate? Oh, when you answer first, you claim your recitation, eh? 12 customer per hour. Remember, arrival rate is 12 hour per customer. That is the flow rate, right? So the headway is 1 over the flow rate. Okay? So just 1 over 12. But that one is per hour. The other one is per minute. So you need to convert how many? 60, right? So, okay? 60. All right. So that is just 5 minutes. Okay? So 60 divided by 12, that is 5 minutes. Clear or not? Easy, right? Easy. So you know the headway compared to the flow rate. Huh? Oh, how about this? A survey in the highway revealed that the average inter-arrival between cars is 2 seconds. Oh, if 2 seconds, what is the flow rate? In cars per hour. Yeah. This is usually, they call this saturation flow. In traffic engineering, this is called saturation flow. The number is usually around this number. How much is the number? One hour is how many seconds? 3,600. And then this arrival rate is 2 seconds. So that means the flow is divided by 2. It is 1,800. Okay, so you remember this number. Okay, if in the intersection, okay, in the any intersection, usually, okay, between 1.5 to 2 seconds. Okay. When the green time, okay, in the intersection, you have a traffic signal, right? And then there is a green time, okay? In the beginning, they will release, but after stable, meaning not from stop, okay? And then you are in the end of the intersection. So I will draw that. So this is supposed to be your intersection. Okay, you are observing here. Okay, so in the beginning you have a long queue, right? So after they pass, okay, all of this pass, later on become stable, right? When they become stable, okay, the headway in the beginning is like this and then going down. Yeah? It will become stable like this. Okay? That stabilize of headway, this is okay. When you convert it into about this convert, this is time, yeah, and this is the headway. It's right. So headway, and you understand that headway means the inter-arrival time between to bumper. Okay, so this is about 1.5 to 2 seconds. The stable one. Okay, that means that is the actual. This is called saturation flow. That means if the traffic signal is actually all green the whole hour, imagine that. This is an abstraction. If the traffic signal is actually green for that flow for whole hour, that 2 seconds mean you will pass only 1,800 cars per lane. With that number, you can start imagine how many cars per hour. Then you can start to see how many lanes you need. Okay. That is only if all green. But in fact, the green time is not full, right? So you probably divide among the other phase of the traffic signal, then it will go down so much. So if you have only 2 phase, so probably around 800 to 900. If you have 3 phase, that means only 600 vehicles per hour you can pass in one lane, one direction. Okay. We will calculate the delay very soon. Okay. First, I will talk about the arrival and then the service, and then I will talk about delay and the queuing line. Okay. This is exactly what we will discuss today. Okay, very good question. Yeah, ahead of time. So, okay, this is question a while ago. Let's do a survey. So this is probably for you that if you want to check the survey, okay, this is the form that you will create. Okay. First, you are talking about flow here, right? So, and this is the arrival rate. Say, customer number 1, okay, arrive between 10 to 10:05. So how many customer arrive? 1. Okay, in between 10:05 to 10:10, so 5-minute interval later, how many customer arrive? 2. Okay, and so on. So say the supermarket here will start from 10 o'clock until 10 o'clock in the night. Okay, and then you divide into 5 minutes, and then every 5 minutes you count the number of customer arrive in that gate. Okay? Or all gate, the same thing. And then this is, say, suppose we have only one gate. So we have an example in here, 539 customer in one day. Yeah, per hour. In one day. One day is 12 hours in this case, right? Okay, this is example. So you have a 12-hour observation, you divide by 5-minute interval. And then from that 5-minute interval, what you will do, you will create what is called arrival distribution, right? So then you count now. Every 5-minute interval is one slot, okay? So now, how many customer arrive in that 5 minutes interval? Okay, so in that 5-minute interval, for example, 72 times happen that the only 2 customer arrive in 5 minutes. Okay, you understand the meaning of this 72? Okay. Only 3 times frequency happen that 4 customer arrive in 5 minutes. Okay. Majority 0, right? Meaning no customer arrived in that 5 minutes. Okay. So you see the total still the same, yeah, 539. Can you see? That is come from the earlier. Can you get it or not? Can you make this or not? So from your survey form, this is your survey form, right? So you need to count, how many customer arrive, right? Say 1, 2, 3, 0. Majority of these are 0. Okay, so then you count How many? Can you get it? The total still the same, 539. So that's the total number of customers. Okay. So then, then you calculate the relative frequency. That is easy, right? 255 divided by 539. Okay. So from that relative frequency, now you get that this is the distribution. This is the probability distribution of arrival. Clear or not? Okay. So then you calculate now the average. How you calculate the average? From the probability distribution, we know this is 47% and then 35%, right? Then you put 47% times 0, 35% times 1, 13% times 2, right? 4% times 3, and 1% times 4. What is that? 1, 2, 3, 4 is the number of customer in that 5 minutes. Clear? So this one multiplied by this one. Clear or not? Okay. So then you get, for example, in here, you get 0.7476 or about 0.75. Yeah. So you get the mean. Okay. This is the arrival rate. 0.75 customer per 5 minutes. Okay. Why 5 minutes? Because that is your survey form. So say you don't like 5 minutes, you measure every 10 minutes, that's fine. Then you get how many customer per 10 minutes. Okay. Clear or not to make that arrival rate and distribution and so on. And then you check, okay, whether this is actually Poisson or not. Yeah. This distribution is you check. Okay. So how you check here? This is the probability distribution of Poisson, right? This is the theory. Yeah. You know this in statistics, you learn that. Eh? So, what is this? Lambda is the arrival rate a while ago, this one, 75, okay? And then E is the exponent. Eh? X is any number that you want. So, 0, 1, 2, 3, okay? So, probability of X arrival in a specific time period. Okay, so let's take example here. So I will name this just fictive Technomo burger. Okay. So suppose we have analyzed the data from customer arrival and found that distribution of is Poisson. Okay. Arrival rate is 45 customer per 60 minutes. That's exactly the same like earlier. Right. So now compute the probability of X arrival during 1 minute period for X equal to 0, 1, 2, 3, 4, and larger than 5. So this is just one server. Okay. You see that this is the customer arrive, and then this is the queuing line. This is under being served, and then this is the customer that out. Okay. So you know that 45 divided by 60 is 0.75 customer per minute. Exactly the same as your survey a while ago. Okay. Then you calculate for one by one. Okay. So P0, okay, you put into the formula, mean 0.75 exponent 0 E exponent minus 0.75 divided by 0 factorial, you get this value. Right. Again, P1, you just input again, you get this value. Okay. So the probability distribution of the theory is this one. Right. Then of course, oh, I did not put here. Okay. Then you can check, okay, whether this theory compared to the actual is close or not. Okay. There is a called goodness of fit distribution. Did you learn that? You say using chi-square, you can check, or using KS, Kolmogorov-Smirnov, okay, you can check whether the two distribution is actually the same or not, fit or not. Okay, you can use chi-square or KS. So these are the of statistics. Yeah? Up to here. Is it clear how you get from the data up to you get the distribution, how you fit the distribution? Any question? No question, okay? It's good that you learn statistics already, so very good, huh? Okay, what is this? Why I'm here? Okay, now service, okay? So look at this now, the service rate means the customer per hour. Service time is the second per customer. So be careful, okay? Rate is the flow. Service time is the headway. Okay? So usually what you know is the service time, not the service rate. Okay? So what is service time? The total service time for M customer divided by M customer being served. Okay? So other name is server, channel, counter, supply, and so on. Okay, let's study this. Say you have 2,400 customer. Okay, the total service time is 2,160 hours. So what is the average service time and what is the service rate? Okay, Livy, you calculate the service time. Joy, you calculate the service rate. Rate, what is service rate?
The service time is 1 per 15 hours.
Service time per minute or per second?
Oh, in minutes. So if in minute we convert it to the hours.
Service rate is the customer per hour. Okay, that is the easiest part.
So 4 minutes, yeah.
Correct. Correct. So the service time is 4 minutes per customer. Okay. Service rate is 15. Okay. So be careful when we said mu here. It's not the service time. Okay. It's the service rate. Okay. Lambda is the flow. Mu is also flow. Is it clear or not? Okay, the notation first. Yeah? Otherwise, you will get confused later. Okay. Again, when you talk about the server, you need to identify the server. Okay. How the server is doing. Is it fast, slow? Is it uniform or random? Okay. How efficient it is. Okay. Is it unpredictable or make a lot of mistake, the server? Okay. How long did they work? Okay. Is there any training that can improve their performance? Right? So maybe if they are human, so they are prone to temperature, humidity, working condition, right? So probably if the working condition is better, they will improve their performance. Okay. Next is whether the server are identical or not. Is probably identical here is the same probability distribution. Yeah? Probably not the same rate, but the probability distribution is the same or not. Okay. And then the service time is correlated or not. Okay. Maybe they chat to each other and then they become correlated. Yeah? And then is the service time distribution stationary or not? Over time, okay, maybe the service time is not the same. Maybe they are tired, the service time reduced. Okay. So, this is finished. Okay. So, let's discuss about service time and block time. What's the difference? Okay. Service time will start when the customer receives the service and end when the customer leaves the server. Okay. Block time will start when the customer receives the service and end when the next customer receives the service. So there is a time that the customer needs to finish the work before the next customer arrives, or maybe there is also walking time. Yeah. So service time is totally just representing the start and end of one customer. Yeah? But the block time is between the next customer. Okay, so these are the three common distribution for the service. Okay, Markovian, deterministic, or general. Okay, again, mu is the symbol of service rate. Okay, what is this? The average number of customers that can be served per time period. Again, what is the distribution? Mass Poisson. But when you survey, you don't survey the service rate. Okay, what you survey is actually the service time. So that means equal to 1/mu. Okay, if the service rate is Poisson, then the service time distribution must be exponential. Okay, this is how you survey. Okay, you survey per customer. Okay, so per customer. So in here, the survey form is customer ID 1. Use your stopwatch. Okay, when it's time to be served, when it's start, when is the completion time, and then you can calculate. So here is what we compute. What we compute is actually block time. Okay. Oh, no, sorry. What we compute is actually the service time itself, not the block time. Okay? The service time itself, not the block time. Because you can see here, the time served is 10:01:05, completion time 02:35, right? And then the next customer served is 05:18. It's the service time, not the block time. Yeah, because the customer arrive at the same when they finish, the next customer being served. Okay, so that means between 1 and 2 there is a delay because no customer, right? So this is not block time, this is service time, real. Okay, so service time itself is just minus, no, completion time minus the time being start. You see? Now, once you have this service time, minute and seconds there, then you can calculate the distribution. So to calculate the distribution, you just divide, for example, service time every 30 seconds or every 1 minute. Okay, and then you get the distribution of the customer, and then you take the cumulative distribution. Okay, so this is the example of the distribution of the customer, and this is the cumulative distribution. That drawing is cumulative distribution. So the average of 1/mu is 1.25 minutes per customer. So in this example, that means the mu itself is 1/1.25, which is 0.8 customer per minute. Clear? Okay, yeah. So the one that you survey is the service time. That means 1/mu. The average is 1/mu, not the mu. So from there you calculate the mu, which is 1/that. Okay. Oh, the theory now. Oh, the theory said this is supposed to be exponential distribution. Okay. What is the exponential distribution? This one. This is the formula of exponential distribution, right? The probability that the service time will be less than or equal to the time length t. What is this? This is cumulative. Less than up to t, that means cumulative. Yeah. So the mu you know, then you can just calculate. So okay, I give example here. Okay, the same burger restaurant a while ago. Okay, so order filling process for a single food server can process on average 60 customer order per hour. Okay, compute the mean service rate per minute and the probability that can be processed in say, less than 0.5, 1 minute, 2 minutes. So, okay, the service rate is mu, 60 customer per 60 minutes. That means if you put it into per minute, become 1 customer per minute, right? And then you put it inside that number. Okay, so 0.5, 1, and 2, right? This is the x. Okay, and then you put it inside here. This is the mu, right? And then you get this value, yeah? 0.39, 0.6, 5.8. These are the probability. What is this? This is the cumulative probability. Okay, so then you can compare that with this earlier. This is what you will compare. That's why I compute the cumulative distribution rather than the PDF. Yeah? Is it clear? Livy, is there any feedback, question, comment?
For now, all good, sir.
All good, okay. So now the server have configuration, right? It's a single line, parallel server, or just one server. Okay, if it is a parallel server, is it a single line multi-server, right? Or multi-line, 1 line per 8 server, or multiple line, 1 line for several server, and so on. So is there any configuration of serial server? Okay, or there is an acyclic network, open network, closed network, and some feedback probably, we don't know, yeah? So you need to check the system. And then, queuing discipline. What is this queuing discipline? Describe the sequence, okay, in which the waiting customer are chosen for the service. So this is equal to the behavior of the customer who are blocked. Okay, we will find all the customer busy when they arrive. Okay. For example, when they see that, oh, the customer, the queuing is full, okay, too many customer, then they leave immediately. That means blocked customer is clear and lost. Okay, the queuing is blocked, the queuing system is blocked, then they go out. Okay. There is a possibility again, they will still wait in the queue. The customer, even though it's a long, okay, queue, or in terms of the length, queue length, right? They will still queue. Okay. In that case, the blocked customer is delayed. Yeah, and they are waiting until being served. There is another possibility that they wait in the queue, okay, and then they leave before being served. This is called renege. Okay, what is this? They feel that the queuing is too long. Okay, then they leave immediately. So here are a few queuing disciplines. So the most well-known and the one that we will use is actually FIFO, first in, first out. In fact, you saw last week, I showed you the picture of the police using stick, yeah, to enhance the queuing discipline. Okay, they need to make a FIFO. Okay. Actually, there is no need for that, but anyway. Okay, so look, if you learn queuing theory, you will see that there are many other queuing disciplines, not just FIFO. Okay, LIFO is also used. Okay, what is this? Last in, first out. Example in logistics. Okay, in the truck, the first thing that you put in will be the last thing to go out, right? Because otherwise it will be difficult. So that means in the logistic, the one that if you want to carry things, yeah, in the logistic, you know, okay, based on the destination, you will put last in, first out, right? Okay, 0, what is this? Service in, random order. So the order is random, not necessarily FIFO. Yeah. Bulking, what is this? they don't join the queue upon arrival. That one, the one that I explained a while ago. Yeah, leave immediately. Okay? So the customer is parking. When they see the queuing is too long, they don't join the queue. Okay? Renege. Okay, this means they leave the queue before being served. Joking. Oh, there are multiple server, right? And then multiple line. They move to another line. Okay, they joking. That means they move to another line. Okay, this is possible behavior, right? So loop. Okay, loop is joining the same queue after being served. So, for example, in children playground, okay, so you have a slide. After you finish, you come back again, right? So, or in Disneyland, probably you like that ride, so you will come back again. Okay, priority queue. Okay, we have a one slide special for this. So, it's a special type of customer will be served first. For example, in hospital, right? So, the one that emergency will be served first. In the bank, you have a privilege card will be served first. Maybe you are older people than 65, you will be served first. So this is priority queue. Okay, there are two types in here, PSPO and NPPS. PSPO is preemptive service priority order. Okay, and the other one is non-preemptive. We will discuss this later when we talk about priority queue. Okay. Okay. Yeah, I just discussed about when it's of this non-FIFO queuing happen. Is there any, have you ever seen non-FIFO aside from what I discussed a while ago? Non first in, first out. In the exam, is it FIFO or not? No, right? It's non-FIFO, right? You first in does not mean you go out first. Yeah. So, okay. So is it kind of joking? No. So that means in the supermarket you can switch from one queue to another. Yeah, that means joking, right? So you can switch. Right? Yeah. So again, unless this is FIFO, the queuing theory that I discussed here, except the priority type later on. Okay. So if you are LIFO, zero, barking, renege, joking, and look at, you need to use simulation. The queuing theory does not work. Oh no. Okay. So there are too many things happening. So the queuing theory is only a small part of that theory. You just otherwise you assume. You assume. Okay? Otherwise you will do a simulation. Okay, so next is the output. Okay, we talked about the input already, so we talk about the output now. What are the output? Okay, lambda per mu. Lambda is the input, right? The arrival rate. Okay, mu is the service rate. Okay, so if you divide lambda per mu, we call this rho. Okay, there is a unit for this. The unit is Erlang. Okay, because the founder of queuing theory, right? This is called traffic intensity. Okay. Next, we have a symbol U is utilization of the system. What is this? The percentage of the time that the all servers are busy. Okay. So this is the same as the total service time of the customer being observed divided by the time of the system was observed for arrival. Okay. So utilization of the system is important numbers. Yeah? And P0, what is this? This is the probability that there is no customer in the system. Okay, so this is idle probability. Okay. Pn is the exactly n customer in the system. So this is called state probability. PW is the probability that arriving customer has to wait for the service. Okay, this is called blocking probability. And probably this is the four things that most often used. Okay, this is the delay. There are two types of delay. One is WQ. What is this? The average time the customer spend in the waiting line for the waiting for the service. When W is the average time customer wait in the system. What's the difference? What's the difference between WQ and W? Okay. WQ is the average time, yeah, this is time, waiting in waiting line, not including being served. Okay. Well, W is the average time the customer in the waiting line and being served. That means including the service time. Is it clear or not? Okay. The same thing with L, Q, and L. Yeah? L is the average number of customer in the waiting line. So this is the queue length. Yeah? LQ is the queue length. The same thing with L. L is the queue length, but in the system. What is in the system mean? That means in the waiting line and being served. Is it clear? So with this notation being known, then you can start with this practice. Okay. Say, for example, direct observation of 2,400 customers arrive 200 hours. Okay. Showing the total waiting time was 640 hours. The total service time 160 hours. Okay. So, and then the facility was observed 100 times, where each observation, okay, customer in queue system were counted and recorded. Okay, and then the total number of customer counted in the queue was 320, in the system was 400. Okay, I asked to calculate what is U, W, WQ, and then L, LQ, and P0. Okay. So this is what you know. The total time in the system is 160 per plus 640. Yeah. This is the service time, right? And then this is the total waiting time. Okay, that means total is 800. So the U is 160 divided by 200. What is that? Okay, 160 is the total service time, 200 is the arrival. The total observation time, 200 is the total observation time. Right? And then W here is the 800 divided by 2,400. What is this? This is the total time in the system divided by the number of customers, right? So you get 1/3 of hours, that is 20 minutes, okay, and so on. So you can calculate everything. So P0 is simple, okay, which is 1 minus U, in this case 20%. U is the term of percentage, correct? Actually, when the server is utilized, that means not idle, right? That, okay, that's why 1 minus U, okay? So, how long is the server is being utilized? Okay, 160 divided by 200. So, this is for one lane. Oh, because we don't know the actual system, so the whole system in this case. And this is actually explained per, this is just one lane actually. Yeah. We will show you in a moment, okay, if we have multiple lanes. So now I'm talking about where that queuing formula come from. I will show you in a moment how you calculate the queuing formula later. Okay, but when you do simulation, okay, when you do simulation, this is what you do in the transient. Okay, in the simulation, you are doing one by one each customer how they behave. You will simulate that, and then you will get the aggregate result. Okay, that is the transient. But the queuing theory that we will discuss in a moment, okay, they derive from Markov chain. That means they derive from steady state. It's already in the long-term behavior. Okay, so that's why, okay, of course the simulation can also get the steady state condition, of course, yeah. But that's why sometimes you will see the result of the simulation will be not always the same as the queuing theory. Okay? Why? Because you will include the transient period, unless you jump off the transient period. Okay? So this was my question in 1996 that they don't answer. Okay, anyway, so when arrival rate must be smaller than the largest departure rate, okay, then there is a violation of the steady state condition. Right? A while ago we said, look, arrival rate, when the arrival rate is higher than the largest departure rate, then the queue will keep growing over time and never reach the steady state. Yeah? So when you have using random distribution like this, you keep remember this. Yeah? The arrival rate, the lambda must be less than mu. Okay, lambda must be less than mu. Okay, not even equal. It must be less. Okay. Otherwise, the Q will go to infinity. Okay. When this happens, because this is not this deterministic system. In deterministic system, it's the other way around. Yeah? Lambda must be larger than mu, otherwise no Q. So if you have a society all robot, okay, that will happen. There is no Q unless lambda is larger than mu. But in the reality, there are some random station, so then lambda must be less than mu. Okay, so there is a law in queuing theory. This is called Little law. Come from John Little, so the name of the person. Yeah? So given any arrival and average delay time, the question is how big the queue length will be. So if you know the lambda, okay, and you know the average delay time is the W, right? So what is the queue length L? So there is a formula, okay, relating between lambda, mu, and L. That is called Little law. Okay. So John Little said in equilibrium, this is in steady state, okay, the total inflow is equal to total outflow. When we talk about IFN, yeah, ideal flow network, later on we talk about this also. Okay, in equilibrium, total inflow equal to total outflow. That means the queue length is always equal to the average delay times the arrival rate. Yeah, the queue length L is always equal to the average delay W times yeah. Okay. So you can also put it this way. Yeah? So if O is outflow, E is inflow, right? S is the queue length, so you can also calculate using this formula. Okay, yeah. So this is the Little law, right? L equal to, is that the same? Oh yeah, okay. L equal lambda times W. Yeah. In equilibrium, regardless this is nice, yeah. We don't know the arrival distribution. We don't know the service time distribution. It's always happening. Okay, so L is equal to lambda times mu. How about if I want to know LQ? Right? Then this one also lambda Q. Okay, the same. So in this case, lambda is actually the slope, okay, of this arrival and departure. Okay. What is the implication of this little law? In equilibrium, the Q length is fully characterized by the average delay time and arrival rate. Yeah? Say example, a company order 100 items per day from a supplier requiring 5 days to deliver. That's the delay, right? Then in equilibrium, okay, it will have 500 items to order, regardless delivery distribution. Okay, so if you want to order 100 items per day, right, but they require 5 days delay, okay, then you need to order how much? Of course, you need to order 500. You cannot just order 100. Okay, so basically, delay will give certain system inertia. Yeah? If the order is now cut, yeah, to 0, the inventory will still swell with additional 500 items before actual deliveries from the supplier is cut off. Right? There is some kind of inertia. Okay, so assuming the cancelling order is not possible. Clear or not this one? Yeah. So that's the implication of little law. So let's check here. Say the insurance company have pending pool of 50,000 unresolved claim and settle only on average 25,000 per month. Whoa. So the question is, what is the average time claimant have to wait to receive the payment? Oh, what is this? Huh? If you don't know the title here, you can solve this using a little law, right? What do you have in here? 50,000 is the Q length, okay, L, this one. Yeah? What is this? Average 25,000 per month. What is that? The input, yeah? So that is the lambda, yeah. So what do you want to get? W. Can you calculate? Huh? L equal to W times lambda. So then W equal to L per lambda, yeah. You see? Yeah, so it's just 2 months, right? Okay, so in 2012, I published this, yeah, and after that, people start talking about it, and the Wikipedia about this, and people in New York use this also for doing the toilet service for homeless, okay, and so on. So these are the example I give you. So basically, this is very simple rule of thumb, okay. I just base it lambda must be less than mu. Okay, what is lambda? Lambda is basically number of customer per time. Must be less than, what is this? This is the service time, yeah. The tau here is the service time, right? And then times the number of server, right? So then you can calculate number of server. Right? Is that correct? So divide it. So then you can get this formula that you can check. Yeah, I will give you example. Okay, say this is the real world example last time. Okay, so the homeless shelter of 500 residents, okay, they have only 10 showers. on average, the person need about 6 minutes to take the shower. Okay, in the peak hour, it's about 3 hours in the morning because these homeless also need to work. You know, they're just homeless because they don't have house. Okay, so the question is how many bathroom actually needed. Okay, so if we use this, we can get the demand is 500. Okay, they need 6 minutes, right? And then because we put it in minutes, so this hour must be put in the same unit. So that means 3 times 60, right? So the total is 16 point. So we need 17 bathroom actually, but they only have 10 shower. So the city government needs to build 7 more bathrooms. Otherwise, the queuing is unbearable. Okay? Within these 3 hours, they need to queue too. So look at this. This rule of thumb that I developed is actually the worst case, yeah? not the good part. Yeah? So if you, in fact, this is like the boundary. If you are doing S in here, this is still bad, okay, not good queuing. But if you less than that, that is really, really bad. Okay? So this is the most important part there. Okay, so later we can discuss one slide special about this. So this is the summary of this first slide, the basic. So you can use as first approximation, okay, that rule of thumb. And then remember the service mean time is just reciprocal of service rate, okay. And the theory that we develop in a moment is just about the limiting distribution on the steady state condition. Yeah? And there is a John Little law that they call this fundamental queuing formula that relate L equal to W times. Yeah. Oh, up to here, is there any question? Okay, which one? Oh, the 3 hour. So basically, this is represent the performance. Okay, this represent the performance. So why we need to use peak hour rather than off hour, right? Because this is the one that in this situation they need to finish within 3 hours. Okay, for example, they start at 5 o'clock. Okay, until 8 o'clock they need to finish the bathing, right? Otherwise they cannot. They will be late to go to work. Right. So in that case, you set this. In this example, you set this performance. But the other way around, you can also put S is down. So you want to know the T, then S is in here. N times tau divided by R. Then you also know. You can use this formula is algebraically. You know? And the nice thing about this formula is now you don't need computer. You know, you can just use calculator or just actually calculate by hand. Okay. Again, this is rule of thumb. Okay, this is the worst case, not the good one. Okay.
Basically from this formula we can get like in the peak hour we at least need like 70 to get everyone.
Yes, in the if you have 500 residents, you need to have all. Okay, okay. In that, let's do the next slide is about this one. So I will explain about this more detail. Yeah? Where is the slide? Let's talk about it in more detail. So I give you a lot of example after this. Yeah. Okay. Can you get the slide in Lentera? The last slide there in the. So queuing rule of thumb. Okay. So this is what we will discuss. Just how you will eliminate or reduce the queue. Oh, really? I think you have. Yeah, that one. Okay, so I will put it up so that you can use. Really? Is it different? I cannot tell. Oh, this is like the last time. Okay, I will update later. But anyway, this is like the last time. Oh, okay, this is the same. After page 25, 24 is the same. Okay, so I will update later. No problem. So again, this is the same thing as before. So this is actually I'm supposed to create can you see my slide? Yeah, this is the MMS. Okay, in MMS, this is the utilization factor. And you look at the formula, yeah, quite complex. Okay, quite complex. Have factorial, right? So this is come from the Markov chain. Yeah? And then after you first you need to calculate the P0. This is the idle time, probability of idle system. And then from the P0 you calculate the LQ and then the L and then W and so on. Okay, so my point is, look at this U equal to 1 over S times rho less than 1. This is the one that I use to derive the queuing rule of thumb. Okay, so you know that rho is equal to lambda per mu, right? Okay, so here it is. So you know U is less than rho over S from MMS a while ago, right? So, and then from here, I can say rho is equal to lambda per mu. Lambda is equal to N over T, right? And then mu is rate, right? That means 1 over R. What is R? R is the service time. Okay? Mu is the service rate. So service time is 1 over R. Okay? So if I put all this together, right, I can say, look, mu is lambda over mu. Rho is lambda over mu. Lambda is N over T. Yeah? Mu is 1 over R. So I can put this N R over T, right? But mu must be, rho over S must be less than 1. So that means rho over S must be less than 1. So I put this. So this is the actual formula. This is the one in yellow. Can you see? Okay. From there, you can just put it there. You can get S must be larger than N R over T. Okay. Clear, right? The derivation, where it come from. So, okay, so you can check the units. Okay, this is the bathroom a while ago. So this is what happened this is what I proposed last time. This is real world in Ateneo campus, okay, in the grade school. So this number is also real. Okay, so they have morning peak every 6 o'clock until 7:15. Okay, in that grade school, there are 4,500 cars will enter that campus. Okay, then there is always delay that they cannot drop the children, and then they said they are late. Okay, so what is the way to solve this problem? Okay, so I said, look, the dropping point, I checked. Okay, the dropping point just required about 60 seconds because each children will bring some kind of luggage. You know, this is a expensive school, so they bring heavy luggage. So about 60 seconds. That is including the maneuvering. Yeah. So each car require about 10 meters to stop and maneuvering. Okay? From entering to the stop and then going out, right? So the question is, how long the dropping line so that the children will not be late for the school. Yeah? So this is what is this? This is the T, right? The time. So the time is only 1 hour and 15 minutes. What is this? This is the N, right? And you know this is the time, service time, the R, okay? The service time, okay? And then, what is this 10 meter? This is the actual server. Okay? The server, one server is 10-meter length of the dropping. So people don't realize that the server is not necessarily human, you know. Just a line, just the dropping line, that is a server for taxi, for car, okay? So you create a meander, okay? So dropping off, yeah, this is the exact like this. So dropping off points like this, okay? They drop in here. So you can calculate, okay? You only need 75 minutes, right? 1 minute. So server is 10. So S is actually 4,500 times 1 divided by 75, that is 60. Okay? So 60 server is needed, right? For that demand. That means one server is 10 meter, that you mean you have a 600 meter length. So I asked them to create a meander, and it works, right? Based on the theory, the theory, we put it into practice and it works, really. This is amazing. Yeah, this is one project. Okay? Is this clear or not? The point is, look, the server, okay, can be parallel, right? And they are actually just drop off points. Okay, this is actually happening in Surabaya in Shangri-La Hotel. Okay, 2009. Okay, during that conference, international conference, 1,000 participants have lunch together. Okay, the participant will queue to get their own food from two sides of the table, right? And then each person require, I checked, about 45 seconds on average to get their own food. Okay, prasmanan. So, question is, how many tables of the same food are needed to let the eating time finish? Because the conference time, lunch time is only 30 minutes. Okay? How many tables of the same food is needed? Look at this. The server here is not the person who served the food. Okay? The server here is the number of tables. The parallel server. So, if you start to realize the server is not necessarily human, okay? Can be length, can be number of table here, right? Can be certain things, okay? Then you start to see that you can actually solve the problem easily. Yeah? So what is this? N, right? 1,000. Yeah? And look, the table also have two sides. That means you can just divide by 2 later on. Okay, so we have N is 1,000. The time that you require is 30 minutes. Right? Each table have two sides. And the time to finish is just, this is with R, 45 seconds. So the server itself is two sides, so I put 2S in here. Clear? Okay. And then I put this inside the formula. And because this is seconds and minutes, so I need to multiply by 60. Okay. So you get, this alone is 25, that divided by 2. So I need 12.5, that means 13. So we need 13 tables. Okay, for 1,000 participants. If you provide 13 tables, they will finish in 30 minutes. Okay, guarantee. Okay, But if you put less than 13 tables, they cannot finish in 30 minutes. Again, what is the problem happening is they don't know that the number of tables is the actual server. They thought the number of people who serve. That is not true. Okay. The same sometimes in the gate. Maybe I have that example. Oh, this is okay. Tell me, school registration. This is also happening. Okay, real world problem. So the grade school of 10,000 students. Okay, of certain day of registration, and then they need to pay the tuition fee, right? I don't know why they still doing this. They did this. Okay, they did serial server instead of parallel server. They did serial server. That means first they need to get the registration form. After that, they check all the delay payment. After that, they pay the cashier, and then they get the payment certificate. So there are 4 stages, okay, of serial server. And then 1 working day is from 8 to 5 minus 1 hour lunch break. Okay, and each parent need to about actually 36 seconds. Not so long, right? It seems like not so long. My question is, how many days is needed to register all these students? Look, if you look at the number, it's 36 seconds. It seems like not so long, but this is 10,000 students. Okay? So the problem is this. Because you have a serial server, it looks like you have many servers, but actually they are in one line. After this, you go to the next. After this, you go to the next. That is serial server. The actual server is actually only one. Remember, don't do serial server. You need to do parallel server. When you have many servers, but they do in states, that is the same as one server. S is equal to 1. Okay? This is what make me frustrated because they don't understand this is the meaning of serial server and parallel server. So N is 10,000, T is 36 seconds. Okay, 1 day is 8 hours, right? That means 20 multiplied by 3,600. You have 28,800 seconds per day, and put all of this into the value. Okay, T must be 360. Yeah, divided by 28,800, you have about 13 days to finish this registration alone. Unbelievable. Right? So all happening just because serial server. Do you realize the meaning of parallel and serial, this one? So when you do serial server, okay, whatever server you had, so many in the queue, in the airport, in any, they're still thinking of the staging. Okay? That is the wrong way of doing queuing. Okay? This is the one that I want you to deliver to many people. Okay, realize that this serial server is actually only one server, whatever number you have. Okay, so you need to make it parallel, not serial. Okay, so here, just remember 500 for each service. Okay, after worship service, there is a clearance of 30 minutes before the next service. Wow, this is very popular church. Okay, the worship room have 2 doors. Each door have 2 meter width. Okay, so now I'm telling you, what is the server here? The server is the door width. Okay, in pedestrian, the server is the door width. Okay, so each pedestrian can pass the door with 0.5 meter width. Okay, the crowd speed is 0.1 meter per second. Okay, so question is 30 minutes enough or not? Right? So again, you get N is 500. Okay, you have 2 doors, 2 meters width. Okay, So you divide by 0.5 meter per pedestrian. That means 8 pedestrian, okay, per door, per S, this one. The total S is 8. The speed is 0.1 pedestrian per second. The R is 10 seconds per pedestrian. Remember, this is just the other way around. So easy, right? This is just based on the unit, you can check. So the T, it must be larger than this. So you check, N is 500, you put it inside. You get 625 seconds is about 11 minutes. Oh, less than 30 minutes, okay? So they will finish, so it's okay. That means they can clear. These 2 doors is enough. Nice or not? Is it something useful for you? So you can check, okay? Think about it. What is the server mean? Okay? And create the spiral server. Suddenly you can solve many problems. Is it time? Oh, okay. So no, server is not necessarily human. I give you many examples here, right? The server can be door width. Okay? The server can be number of table. Okay? So once you start to realize what is your server, then suddenly things change. Okay, so I will stop for a while, for 1 hour for break. Last break. Okay, let's start again. Okay. Where were we? Here. Okay, so this is our last discussion about door chart. Right? The actual server here is the meter width, yeah, of the door. So in that case, you can also expand the door width rather than just the number of doors, right? It's the same thing. So in fact, these are the example of, okay, let me share with you. This is the example of experiment that I did, yeah, together with my students. Can you see it? This is in YouTube, so posted by my student. Yeah, this is me. Right? So you can see. So we have 100 of students. Yeah, and I require them to wear red hat so that we can track them. Okay, so this is the on the right side is the tracking of the blocks. Okay. And we have yeah, that evening we have many experiments going on. This is just one of the examples. So this is other example of the experiments. And, we are trying to track them computer vision. And we want to know whether we can track them correctly. Yeah. The numbering is the important, how the polar rate. Okay, so these are the example. Yeah, in fact, my previous lab was called pedestrian and traffic computing. Anyway, so I have a queuing tutorial in Refuledu. Okay. The one that we discussed today is actually all in here. Okay, so including for example, the arrival, distribution, right? The survey form a while ago, so exactly is in the tutorial in my website. Okay, and inside here also you can have several calculators that you can use. Okay? So this is the rule of thumb queuing calculator a while ago that we discussed. So of course this is, and including the examples also in here. See the school registration, right? The morning pick. So is exactly the same as my slide. Yeah, over time I expanded this. In fact, several teacher from or professor from different university, including MIT, also using this website because quite a lot of effort I make for this calculator. Okay, so let's continue. Okay, with the slide. Okay, so here is the role of specialization. Can you see? So now can we use rule of thumb to compare which one is better? Okay. So 6 person doing specialized tasks in a series. Okay. And then say the average time is 30 seconds per customer. Why? Because they are specialized, highly specialized. So they are well trained in this case. So each person are well trained for their own task. Okay. And then this is proposal A. Okay. Proposal B is parallel server. Okay. The average time increase because they are not well trained, because they're not specialized. So the average time increase become instead of 30 seconds now become 90 seconds. Yeah. 3 times longer because they are not specialized. Right? Of course, when you are specialized, you can handle better. Correct? Okay, so that's why faster in giving the service. And if you are not specialized, so in here I just assume 3 times than the specialized. But actually, not as worse as this, but I'm just making it worse. 3 times. What happened? Okay, so let's say you have T larger than NR over S, right? So N we don't know, so we don't care about this. So then you will see that if we put in, right, R is 90 over 6. Because it's parallel server, so you have 6 server. Okay. But because of serial server, this is what many people don't realize. Serial server is basically just one server, okay, regardless number of people that you put in. So then 30 seconds divided by 1, that is actually 30n. So in here, I can just prove mathematically, right, that specialization is not necessarily good. Okay? Of course, specialization is only good if the service time can be decreased so much that then as the number of serial server itself. But in general, you can see that parallel server here is performed better, 15 rather than 30, yeah? Twice. Even though the service time here is actually 3 times, right? 90 is 3 times of 30. Okay, so I hope you can start to help me in make other people realize, okay, the importance of parallel server. Okay, what people don't realize is they think they are doing parallel because they have many servers, but the way of staging is actually serial server. Okay? So here are the summary that I already mentioned. So the size of tables can be parallel server. Okay? The length of dropping points, right? The length of meeting points, number of vehicles, and the capacity itself. For example, elevator. Okay, probably you are in the university. You start to see the number of elevator and its capacity is actually the server. Okay? And then the door width. Okay? And the number of people, sometimes the server itself is a human, so the number of people really matter. So, right. Okay, so before this, is there any question about queuing in general, the queuing rule of thumb? Okay. The message is simple, right? Start with simplification. So rule of thumb is in here is just simplification. Okay, not the actual queuing theory formula. But at the same time, this will help you to realize many things. Okay. many people said, okay, to do parallel server, then I will do self-service, right? Actually, that's the best. Okay? Self-service is the best because your number of server is infinite. Okay? Infinite means because your population is infinite, the customer themselves is the server, right? That is the actual things that's supposed to be the best. But many, what they call a self-service, okay, including self-service restaurant, ATM, okay, or the service gas service station, they are not actually self-service, okay, in terms of queuing. Because why? Because in gas service station, the gas pump is the server, okay, and in self-service ATM machine, the ATM machine itself is the server, right? So they are not really self-service. Okay? But when you put the same thing with the self-service restaurant, the tables of the food on the server. Right? So this is what is self-service actually, okay? And this is the ideal self-service. Say you are doing a driver license test, then you do all together at the same time, right? So the server is actually the one who take the exam. Okay? So that is a parallel server. Okay? So during my pedestrian experiment that I showed a while ago, okay, there is what is called activity hours, okay, which is probably only 3 hours. During that period of activity hours, so I need to do all these experiments. We have 15 experiments, but the bulky part is actually distributing the form, distributing the material, including the hub, the red hub. Okay. First time I put several. Okay, my assistant at that time. So doing parallel server. Okay, they do several tables to distribute. They need to register, fill up the form of consent that they join this experiment, okay, being tracked with the video, and then of course I give them the hub. Okay, but at the same time, after probably 15 minutes, I realized this is not possible to finish in because I just calculate. Right? So it's not possible to finish in 2 hours just for registration alone. Okay, so then I said, look, this is a problem. So we need to finish because we have activity hours is limited. So we need to finish the registration as fast as possible. So how to do that? I created a self-service. How to do that? Go to the classes. Okay, I asked them to go to the classes, and then instead of one by one or several server here, and then they will fill up one by one and then queue. Okay, in the class. It's a really parallel server because we just distribute directly in the class and then they fill up the form at the same time. So this is an example of self-service. Clear, eh? So the same thing with the online service is basically this is the pure ideal self-service. So if you can ask the people to fill the order form in the internet, okay, at any time, so that is self-service. Clearly, self-service is where the customer actually doing serving to themselves. Okay. Partially true in this example, okay, they are doing it themselves. But in terms of queuing, no. Okay, because the actual gas station and the ATM is actually the server here. Okay, so. While when you order in the internet, your handphone or your computer is actually the server, but you do it themselves. So there is a queue to enter the server itself, but in terms of the bit rather than you personally go to that place. So in that case, become online service, become self-service. Clear, yeah? So try to do online service as much as possible. So with that, we go to the next topic, which is how to actually reduce or eliminate the queue. Okay, so how we can reduce or eliminate the queue? Is it possible or not? Right? So many people said, "Oh, it's not possible." That's not true. Okay, so I think we have discussed this earlier. So I just skip. Here it is. So the technique is simple. Okay, you need to separate physical things that you want to transfer and information that you want to transfer. So remember, in my generalized queuing definition, right? So it's a process where things need to wait for certain times to get the service. So that things can be physical things, which is people or material, or information. So once you start to separate, yeah, between physical things and information, then you can start to create a better queuing. Okay? So why? Because physical things cannot be transferred through the internet, right? Okay. Now the critical question is: does the system need to transfer the physical things or not? That is really critical question here. And of course, you need to know: is this information or this is actually physical things? And not as simple as you think to separate them. Okay. Here is the step to do a queuing analysis. So number one is important here. Number one question is the queue necessary or not? Why do we queue? Okay. If it is not necessary to queue, okay, make a system so that they will not queue. Okay. So separate the information from the material will help you to understand whether the queuing is really necessary or not. Okay. Physical things, yes, you need to queue. Okay. But my information, you don't need to queue. Okay. Number two is actually identify the server, and then you not need to brainstorm the solution. Okay. Of course, easy, right? Because you know four variables inside the queuing rule of thumb: S, R, N, and T, right? You know, we want to increase the number of servers. Yeah? We want to increase the service, reduce. We want to service rate increase, the service time reduce, and then you want to reduce the customer. So this one must be reduced, not increase. Yeah? Service time you want to reduce. Right? And the time period to serve, of course, the performance, yeah, you also want to reduce in this case. Yeah? So, yeah, service time you want to reduce, right? Okay, so then you check, okay, what being transferred. These are example of the list, and who actually are the customer and the server. Yeah. Before going this, I'll come back here later. Okay, here is the actual discussion I want you to think. What most people think as material, but actually just information.
Material for this information.
Okay, my first example, money, information or material?
Material.
Material, because you can see the money, right? Okay, money, okay. So, look, this money is not the real money, okay? The real money is the information embedded in here. The money is practically information, not the physical things. So in that case, if you want to pay, use online service to pay. Develop an online service of payment rather than pay directly using real money. In fact, in China, there is no more money, physical money. Okay. Okay. So money is information, not material. Once you realize that, then all the payment, don't pay in the actual things, with your material, transfer of a bill or a coins. You start to realize when you do online registration and so on, transfer via internet, because money is information, not material. So is queuing necessary? No way. Queuing to pay, that is not correct. Right? Because, why? Because money is information.
Information.
Realize? Okay, my next question. How about this one? Let me put it out. Key. Information or material?
Material.
No, the actual key is information embedded here. You see, this one, okay, this is actually numbers. This is the measurement of numbers that they put inside this material. Okay, you start to realize what is information and material. It's not so easy, right, to realize because you don't used to it. Okay. Okay, what is the implication? If the key is actually information, not material. So say you are having a hotel, okay? Registration, do you need to register? Yes, online. Payment is information, right? Yes, online. Okay? Do you need a log, what is that? The front desk to register, you don't need anymore. Do you need a person to deliver the key? No need. Why? Because key is information. That means when they register, they get the key. Okay, they can just put the number inside. Oh, now start you realize. So a lot of efficient things can be done simply because you know this is information, this is not material. Right? So you remove a lot of what is that? Inefficiency. Correct? Okay, now you start. So money, the key. What else? Okay, tell me. Student ID, very good. So ID is information or material? Information, okay? ID is actual information. So you don't need to have a card. Those card is just to show your information. You don't actually need that. In fact, all the government paperwork, including the license, okay, all these studies are just information. So all government services, no need to be coming to the government office in person. You don't need to. You start to realize that queuing is not necessary anymore. Now you start to realize. So why I oppose offline education? Okay, so this kind of education, okay, do we really need to meet in person? Material or information? Information, okay? Don't need to come offline. So, look, I discussed this many years ago, even before COVID, okay? So I started maybe 2008, 2009. This. Every time I give seminar, many times people will look at me. They said it's possible. Okay? During the COVID, they do all, and then they said possible. See? Why? Simply because this is actually information. Okay? Many jobs. What they do, they are actually delivering information. There are several jobs that are not delivering information. I know. Construction worker, cleaning service, okay, food, for example. They are not information. They are physical things. So they still need to travel. Okay? Can you start to realize the future? Can you start to see the real future that you use? Because I'm trying to open your mind, okay? Okay? Now start to realize what is the implication of internet. Before internet, okay, people don't realize this. The actual COVID pandemic will start to make people realize. But unfortunately, many people, including this in the university, yeah, they don't realize the meaning of this. Every time I talk like this, people will start to oppose me, telling that, oh, no, you still need to do offline. Look, this is not the future. This is backward. You see? Okay? Material or information? Information. Oh, information, you just use internet. Okay? Don't just use, if material, yes, you need to be there. Okay? So, in my dream, okay, I'm talking about my dream now. Okay, in 1990s, I was thinking about the dream. That I want to create a very simple logistic system using your pressure, similar to what Elon Musk is doing. Okay, but for delivering goods. That means that every time you push one button, you can just sending the goods from the factory directly to your house. Okay, so what does it mean? Meaning that in the future, yeah, I'm talking about future here. In the future, the technology will start to think, will start to transfer, okay, what is information and material. The material things will really become the material. The actual information of it will be separated from that. Okay, and then you start to see that there are partial information, there are partial materials that you can start to separate them. And then the information will be delivered by the actual internet, while the physical thing probably will be done by the robot. Okay, I give you an example. House, material or information? Okay, material, of course, right? But when you build a house, okay, when you build the house, construction worker, you are telling, okay, construction worker need to be there because they are actually delivering materials, right? But look, partially, okay, yes, at this point, yes. But look at the future. Okay, when we have a 3D print, right? The future of a 3D print, the design is actually information. So you can design it, okay, the information, and then you can deliver that design, okay, to the 3D print robot, and they will build the robot without construction worker.
Wow.
Wow. Okay, because separate the information from the material. Hard to see or not. Exciting, right? The future that you see. Okay. Oh, okay, now tell me, what do you think? What is material? What is information? Yeah, eventually at the end everything will become information. That's true. Wow, you're very smart indeed. Okay, so for example, is a kiss or a sex is actually information or material? Both of them are actually information, right? So in the future, I'm not saying about now. Yeah? In the future, this can be a remote marriage, okay, because of the tool that we can create. Huh? Because deliver exactly the same taste, the same information that you have. Okay, so I'm not talking about now. Okay, I'm talking about the future. So that will create a new impact, new way of thinking, new kind of family. At this point, for example, doctor is delivering information or material. Example, surgeon, right? So nowadays you can see that the surgeon is doing remote surgery using internet. And then the one that really doing the surgery is actually the robot. You see, you can start to see that. Can you see that or not? So queuing theory is not just queuing, you start to see in different way of thinking. Is this something in the future? Yes, this is something important, right? So this question that I stated a while ago, do we really need to queue? Okay. So is queuing really necessary? That is the basic fundamental question. Why do we queue? Do we really need this is necessary or not? Once you ask this, you start to become frustrated, because you know this is not necessary. Why you are still doing it? Because you have a solution for that. But they are headache, they don't want to do this. Simply because of the tradition or probably because of the way of their thinking that is so traditional. Okay? That's why I start to teach this. I hope, this is my hope only, so you can help me to spread the word and start to change the way of thinking of other people. We will have better world, real, right, without queuing. In fact, the government is starting to, always expanding the road, right? The lane width is actually the server, right, in the road, right? So they expand, they do road widening. They demolish a lot of houses, nah? Why? Because they want to expand so that people will start to travel. Look, this is actually not the way to do. Why? In the future, you don't need to have this. Because once people start to realize that this job is information, this education is information, we don't need to travel anymore. Right? We don't need to travel anymore. So the one that travel is actually for delivery of logistics, the goods, the food, okay, the material that you need to travel. But going to school, going to work, which is mostly information, you don't have to. Is this queuing necessary? No. So that's why I said this is fundamental question. Okay. I hope you start to realize. Okay, tell me your thinking. I want to have a better discussion in here. Leafy keep laughing. Is this blow up your mind?
Suddenly this thought come to my mind that I think that actually pregnancy is also like information, right? Because
Information.
nowadays
Correct.
I don't know, yeah, because nowadays there's a technology in China, right, to grow a baby without a woman being pregnant, so they just can grow it in
Correct.
the incubator. Yeah.
Correct. So it is possible, right? So in fact, the change of DNA, RNA technology, CRISPR, for example, this is change the world, correct? So again, all of these are information, right? So you can create babies using information. Okay, that's exactly what there's a movie about this. Okay, I have mother. I don't know. Yeah. Okay. Okay, robot with information that create babies. Eh? So again, yeah, once you start to realize separation of information from the material, and basically everything will become information at the end, right? You will see many things are basically once you have the robot is technology becoming better and cheaper. Okay, so people will go to this trend. I'm talking about the trend of the future, which you can predict because it's simple as this. Because you know there is a separation between information and material, and the material can be delivered by the robot, the information delivered by the internet.
Mm.
But I think it will be very, very, very like difficult to rapidly grow in Indonesia because actually queuing makes money here.
Queuing make money is probably because they want to create perception.
Yeah.
Okay, so that is also possibility. Queuing make money because uh, when when you create a problem to other people, they will get some kind of corruption money. So that is a possibility on that. But again, I'm talking about that is the job of the game theory for the corruption part. Okay, but in the queuing part, I'm talking about the efficiency, okay, of the system that we can improve. Okay, so the game theory is the one that talking about how you manage the performance, no, so that the corruption can be eliminated. You know? But in here, no, it's not the domain of that corruption thing. Yeah, we are talking about how we will create a better, efficient system.
Mm.
But based on this thinking, suddenly you start to realize many things, right? Why until now the job, the education still offline? Okay, even though they only deliver information. So my guess, okay, number one is because of the monitoring system, there is no trust between employer and employee. There is no innovation in the management system, right? Because of lack of trust between employer and employee, so then there is no innovation in the management system, so they cannot monitor to each other. But actually, there are technology already there. For example, you can install camera, and you only work, okay, when your camera is actually open in your house. Then you can actually do all this online job. You know, again, it's a matter of management system that we can create rather than the necessary things to queue. Every day, remember, this is actually the most stupid things human do in this century. Every day we go to work 1 hour or 2 hours to go to the work, is right? Or to go to school, yeah. Traffic. I mean, doing repetition thing, you know. You go to the same place, okay, and then go home again. Right? So you repeat the same thing and you don't like it, but you're still doing it. Isn't it? I'm talking about the human society here. Okay, that we keep, and then every day you do exactly the same, and then at the same time, so you queue. There's a traffic jam there. Oh my goodness, this is and you repeat the same mistake. I mean, just one time, right? Repeating the same mistake for almost one whole life. Isn't that very funny? To think of that, okay? How funny is human being? So if you think say you are from the other planet and you start to observe how human, you start to see something very funny. Why we keep repeating the same problem? Okay, so I hope this lesson of queuing theory make you realize many things. Yeah? Yeah, opening your eyes. Okay, so okay now I'm discussing here about economic. Yeah? So how do we hotel logistic or good distribution as a queuing system. Okay, I mentioned earlier, say from factory, okay, this is one server, right? And then go to the distributor, to the retailer, merchant. And if you look at this, each of these distributor, retailer, this is actually a queuing server. And my question sometimes here, this is actually hierarchical system, isn't it? Hierarchical system. Yeah? How many server do you need, actually? Okay, and do you need to have a very long hierarchy, or actually spreading like this? Okay, so and then what happens if you cut short from factory directly to the customer? Yeah. It is possible, yes. Okay, with the internet, it's possible, right? So this is flat para server, right? So question is, how many server do you need, right? And the next question is, what system is more efficient? Which system is more cost effective? That's actually you need to compute, right? So, okay, I'll give you a story. Okay. In a parent association, okay, so when they have small kids and they have meetings, okay, they give food. Okay, after the kids are dancing in front, and then we have a gathering to eat for the whole school. Okay, so each parent sit in certain table. Okay, and then what happened is during the eating time, okay, we need to queue in the tables as the usual. Okay, we need to get the food and then queue in the table and then put in our own table and then eat, right? Because the number of servers, the number of tables are limited, okay, they don't understand the queuing, right? That they don't understand that the queuing table is actually the server. So, and it takes so long, okay? The performance of the kit probably only 1 hour, but queuing for the table is about 2 hours already. So after eating, okay, I was very thirsty, right? And again, they have one dispenser only. One dispenser only, okay, for hundreds of oh no, right? This is a really problem because, you know, you already eat and queuing very long, and then now you are very thirsty and you need to queue again, maybe another 2 hours just to queue for the water, right? So, knowing the queuing theory, so I give a suggestion how to solve this problem, yeah? So, you know how to solve the problem. So I asked the one server, okay, do you have a jar? I said, do you have a jar of pitcher of water? They have said yes. Do you have a jar, pitcher for each table? Say we have 10 tables. So yes, they have. So fill up that pitcher of water with the actual water. So only one server selling, and then you distribute to each table. Okay, you distribute this pitcher of water to each table, and then one table consists of 10 people. They will deliver to their own glass, rather than whole people, hundreds of people queuing to one single dispenser. What is this? This is hierarchical system, isn't it? Exactly the same as logistic model. Okay, instead of one server serving all with long queue like that, you start to distribute, okay, to say from the factory to distributor, and then distributor go to retailer. Exactly the same, right? Hierarchical system. Okay, so that's why when you some people will say, oh look, I want to cut short the middleman. In fact, the middleman, the distributor, the retailer, is the one that makes it efficient in terms of the economic system. Okay? The trader is the one that makes it efficient in terms of the economic system. Okay? Yes, you can cut short this directly. Okay? That means you need to have a very big parallel server in that factory itself. which probably not necessarily efficient. Okay. So again, using this kind of distributor, the factory need to handle only maybe 5, 10 distributor rather than 100 or 1,000 or million of customers directly. Can you see that? Okay, so middleman in the economic system is not necessarily bad. Okay, if you think in terms of queuing system here. Okay, because they make the system more efficient at higher cost, yes. Right. But in terms of efficiency, not necessarily bad. Okay. Can you see that? Okay, so this is just I want to connect between economic and queuing, yeah, which we can model that. Okay, so what else? So here it is. A while ago I said, by identifying the material from the information, we might be able to transfer material queue into information queue, right? So you can start to separate them. Now you can eliminate the need of material queue, okay, by, for example, work from home, okay, online learning, online meeting. So no more traffic congestion, okay. Say removal of hotel registration. This is just one example. So these are basically you can eliminate the queue, not just reduce. You eliminate the queue because these queue are not necessary. Okay, and I said the future of queuing. Yeah? So the impact of 3D printer, right? So how do you simply send the design and then the robot will build the house for you, right? The same thing. The future technology will actually change the way we live, right? So what will be the impact if the internet speed is actually very high, and that the internet cost is almost nothing, right? The future of job, the future of school, the future of congestion, no more, right? And the impact of family relationship probably deteriorated, I don't know. Okay, but this will basically change. So the government job nowadays, when they start to create infrastructure in terms of road and so on, probably that is not correct anymore. Okay, what they need to improve is actually the internet infrastructure rather than the road infrastructure. Yeah? In fact, several countries start to combine telecommunication and communication and the Department of Public Works. They should supposed to combine into one department because the internet and the road is actually, they are connected to each other. Can you see that? Once you start to realize this, combining, separating between material and information, okay, then everything changes in the mind. Okay. So again, this is the summary from this slide. Yeah. Okay, so question, discussion. Come on. So what did you get? What did you learn? Is this something interesting for you or very interesting? Yeah? So because with this way of thinking, with this kind of simple model, basically you can start to predict the future, right? Where the future of human society will go. Okay. People start to think, oh, this is conspiracy theory, this is and this and that. No. You don't realize why. Because we have internet since 1995, 1990s. Yeah, we have internet, but we don't really understand what is internet. Right? Until today, we still don't understand what is internet. So we just think internet is just, browsing web. No, it's much more than that. It's a parallel server. Okay, it's an information transfer. Okay, once you start that, realize that this is actually information transfer, and what is information, what is uh, uh, material, then you start to see, hey, many things in our life is no longer material actually, right? Huh? Are you still in the mindset of these things are material? Just last week, I got what, rebuke from the head of the program in other department, not here. Why I deliver online course rather than offline? Very difficult. Okay. I said, you probably need to sit down in my class in theory. Okay, so okay, so let's do the computation, or maybe I don't know. Okay, go to the MM1. Okay, so let's go to the actual computation. Where queuing? Single server queuing MM1. This is fast. Probably, I hope. Let's see. Can you see? Yes. Okay. So I don't review anymore. So this is already finished, right? Okay. This is the assumption. So MM1, what is MMM? It's a Poisson. Okay. The arrival distribution is Poisson. The service time is exponential. Service time, not service rate. Okay. And then the number of server is only one. So this is the basic. So there are many assumptions in here. So you need to realize population is infinite. Okay. Customer arrive and enter facility individually, not as a group. So don't think as a group. Okay. Look, in any model, what you need to understand is the assumption. Okay. After that, the computation is rather easy. Just plug in the formula, you go. But if you violate the assumption, that model not correct. Okay. So assumption, again, arrival rate follow Poisson distribution, service discipline is FIFO. Okay, so the customer must stay in the system until the service is completed. No bulking, reneging, joking, no. Okay, waiting area is unlimited. Okay, the same thing. Yeah? Unlimited waiting area is again impossible, but this is the assumption. Yeah? Service time exponentially distributed. Arrival time must be less than service time. Why? Because if arrival time larger than the service time, you cannot use MM1. Okay. The customer in front is immediately served without walking time. So that walking time is not included there. Okay. Using that, now you have this formula. Okay. Utilization factor is just rho, which is lambda per mu, of course, must be less than 1. Okay. And then what is probably empty system? 1 minus rho. Okay. Of course, right? 1 minus u. Okay. Number of n unit, just this computation. That means first thing you need to do is to compute the P0. Okay. Once you compute the P0, you can compute everything else. Okay. So next. Here. This is probably what you need to do. You want to compute W, Q, and W. This is waiting in queue, waiting in system. What's the difference again? What is the meaning of waiting in queue and waiting in system? What's the difference?
The waiting queue is like the one that use the block the block time, right?
No.
No, it's the
Waiting,
time.
correct. Waiting in queue is waiting to be served.
Yeah, it's
Yes, so waiting in system including being served. Yeah, so entering the system until out. Okay, one person from entering the system until out. That is the average waiting in the system. Okay, in, out. This one is only during the queuing, during waiting only, before being served. Okay, so you can see. And the queuing length and queuing system, average system length is the same thing. Eh? So in queue, and this is including being served. Okay? Clear, yeah? So once you have that, you just plug into this queuing formula, or I have already the calculator, you can just use. Okay? So if you don't like, you can create your own. So this is not so hard to put in. This is all very simple. Okay, so I give you example. So lambda is 0.75, mu is 1. So compute everything, right? So then you can just compute, yeah, plug into the formula. So you can test this, yeah, in that website. Also, if you want, you can calculate in Excel, yeah. Correct. If you have a different model, you have different formula. Wow. Yeah. That's why I put the calculator so that everyone will just use, no need to create, okay? That's why people are very happy with my tutorial. So, because they just use it, they don't need to create a calculator anymore. Yes. So this is the simplest one. So there is no summation and so on. So, but the MMS is much more complicated. Okay, let me highlight something that probably even if you plug in, you will start to realize. Look at this. This is 2.25, 3 customer, 4 minutes, 3 minutes. Okay. So of course, waiting in queuing is only 3 minutes, and then including the service time, 1 minute, right? Become 4. That's clear, right? Because W here is queuing plus the service time. Okay. And here is 2.25. Look, this is the average, remember. Of course, there is no 2.25 customers, right? But this is the average. Okay, yeah. Now, okay, this is the idle time, 25%. That means 75% they are fully utilized, right? So now, what happens if, this is important, instead of 0.75 customer per minute, or 1 customer per minute, I multiply this by 60, okay? So that I get per hour. What will happen? Will the MOE change? Right? Will they change? Look, exactly the same, right? Supposed to be. This is per minute, this is per hour. But the number changes, of course, right? 0.75 and the other one is 45. So, okay, if you calculate that, okay, this is in Excel I can compute. Okay, yeah, actually the same, but the unit is different. So then you need to multiply by 60, or in here divide by 60, nah? Because this is per hour. Okay, but if you put it in multiply again by 60, you will get exactly the same. Okay, that formula is depending on the unit. So be careful with the unit, okay? Okay, and be careful also. This is mean service time mu. Okay, this is mean the rate actually. 60 is customer per hour, not hour per customer. So just be careful with check the unit. That is the most important part. Okay, so I change the unit. Okay, I change the lambda and the mu. Okay, and you can see everything else is the same except this W. right? So this W changed because lambda and mu changed, and basically this represents a different of unit time unit. Yeah. So hour or minute and so on. So now suppose we improve the service. Okay? Of course that is our goal, right? We want to improve the service. So instead of say now they decide to order filler information reduction. So with design management, they estimate the mean service rate increase after the experiment from 60 customer per hour become 75 customer per hour. Then you can compare. And this is the proposed scenario. Okay. The lambda still the same, mu improved. Okay, from 1.25, from 1 now become 1.25. What happened? Oh, look at the numbers here. Earlier, what was the LQ a while ago? The LQ was this one, right? 2.25, 3 and 4 minutes. Here we have 0.9, okay, 1.5, 2 minutes and 1.2 minutes. So the improvement of the input, yeah, little, but the improvement of the output, a lot. Can you see that? Okay, so this is non-linear. Okay, so queuing system is non-linear, heavily non-linear. So then you start to see that a little change in the input will give you a lot of profit actually. Okay. And this is why queuing theory is very heavily used in industry, in the real world because of this. Yeah? The change of slightly change in the input will create a huge, tremendous impact. A lot of profit you can gain from the queuing improvement. Okay, so up to here, I think our class will end and we will continue 2 weeks from now because next week is holiday. But 2 weeks from now, you need to present your work. Okay? And I noticed several of the assignment you did not do. Can you start to check the assignment that you did not finish? Can you? No, you did not. So if you have a problem in submission, you tell me. And if you want to have a notification, did you receive the email? I tested in the notification in the announcement, right? So feedback and the announcement. I just say there is an offer to assignment. Did you receive that? So there is a email system in Lentera that not from the assignment but from the announcement. So I will try to use that. Okay, thank you very much for today.
Okay, thank you, sir.
Okay, enjoy your holiday.